everyone, Alicia Panzarella here, taking a look at some of the questions, results, discussions that came up with my action research project. So like I said, I'm Alicia Panzarella. I'm in the ACTE program, and it is with the STEM endorsement, so focus on that. I am the physics teacher over at Eastern York High School. And let's go ahead and just jump right into really what was the purpose of my action research project. And it kind of starts back with my whole motivation, starting with one of the courses within our program, and it was the engineering course that we had to take. And as I was going through the course, I just found the application of the course content to be so applicable to my own content. And the question started to form, well, how applicable is this really? What could implementing the engineering design process do for my students? So the knowledge that I was hoping to gain was, do students' application of my content and their 21st century skills, so those problem solving skills, will they improve with the implementation of this process, which you can see on the right-hand side, really lends itself nicely to physics, actually really any content, because it focuses on, defining a problem and then going through this iterative process once you define it, where you kind of ping pong back and forth between thinking about the problem, implementing some type of prototype, reviewing your prototype, thinking again, and designing again. So that plays into, do students' overall problem solving skills improve when they embrace this process of going back and forth between thinking and doing? So the problem that I was hoping to solve is how can that engineering design process be implemented so that it can have a positive impact of overall student achievement and ultimately their problem solving abilities? And the whole reason why is because we're all trying to educate the whole child within our content. I don't want them to just be really good at physics or just be really good at applying physics content. I want them to have skills that are going to help them as they go into their next level, especially considering that I teach all seniors. So they really need to start to fine-tune those problem-solving skills as they go into the next step of their life that's going to have a lot of unforeseen questions that they're going to need to answer. So ultimately, my research question was, how does the implementation of the engineering design process impact student problem-solving abilities? So a little bit of background for this project. We all had those 5 papers that we had to look through, and in general, all 5 of my papers did have implementation of the design process and did have positive results. That's kind of what everybody was talking about. So how I started off with this first paper being kind of like my foundation, where this paper identified the 5 key aspects of the problem solving design process. And these researchers actually were in a physics classroom. So their research, at least to me, was very applicable because they implemented this engineering design process with the electricity and magnetism unit, and they did get positive results. So I was hoping to kind of take what they did and then build on it and make it applicable to my classroom. And then in order to do so, these next 2, so the one that's involving curriculum and then the one from 2013 down here, all stressed how can we do this? How can we implement the design process so that it can be effective? So that's what those 2 papers really looked at, what was not effective, what was effective, and then ultimately this paper down here provided alternative findings, which I thought was really interesting. So I wanted to see kind of how their findings then compared to mine. Did we do anything similar? Did we do anything different? Because these researchers actually found that their students generally did not think of the engineering design process in a quantitative matter. They found very positive qualitative results, but not quantitative results. So I really wanted to see, are my students going to show that as well? And it turns out they didn't. So taking all of these pieces, having already seen a physics classroom, that implemented it had positive effects. Well, how did they do that? They had proper structure within their curriculum, and they really reviewed and reflected on it as well to see, okay, well, do we need to make changes now? Do we need to make changes at the end? And I, like many of you, found the same thing that I had to do within my own classroom. So my design focused first and foremost on the in-class instruction. So it was scaffolded where I did kind of build them up to the different parts of the engineering design process, and all of it was lab-based, especially for a course like mine. It lends itself really nicely to just being in the lab most of the time, which is great. So I did have 2 units that I was able to look at. So Unit 3, which is uniform acceleration, and Unit 4, which is projectile motion, all comes together for the final AP exam, which looks at kinematics. So once I kind of structured the class, gave them all the tools that they needed, they dove into the Unit 3 assessment items, which was the parachute construction. So what they had to do, they were given a general question of how can you produce a parachute that is going to have the lowest acceleration when dropped from the top of the stadium. They had to go through the whole design process, and then they had a discussion board where they looked at the qualitative and quantitative aspects. Then they had their lab practicum, which is a lab-based assessment, again, applying everything that we learned into that lab setting. And then once we got to Unit 4, they had another general question of how can you solve a mundane, everyday problem with physics? So how can you engineer something that utilizes projectile motion? And then a sports analysis. So many of my students either play a sport or play a sport just for fun. So they looked at what do they physically produce when they are doing their sport. And then ultimately this came together for an AP exam that does follow all College Board criteria, which means that it was all applying concepts rather than just straight like plug and chug problems. So a little bit of background information, I just wanted to provide this. I did try to provide a numerical ranking to make my quantitative and qualitative data a little bit more precise. So this is the ranking that you're going to see in the next slide. So overall, my findings in general are here. I have a little bit more in my paper, but it did get to be a bit cumbersome. So as you can see, whether it was the lab practicum, the engineering design, the sports analysis, the class averages are all within the 80% range. I did have that the major majority of the students for each one of these different assignments, they were exhibiting rankings of 4 and a 5. So they're not only meeting the expectations, many are going above and beyond, and a large percentage are showing complete mastery of the concepts, the problem solving skills, because they took all of my requirements, not only went above and beyond, but I say that they could also teach one of their classmates if necessary to show that they have that mastery. So we're not only getting pretty high class averages, but we're also showing pretty high class rankings. Now, one thing that I did want to make a note of is this qualitative class discussion. Do notice that those rankings are much lower than their quantitative counterparts. And that's really the big thing that I was able to conclude. So I learned quantitatively, which is much different than one of the literary papers that I read. Quantitatively, the major majority of my students not only meet the expectations, but they exceed the expectations in terms of application of content, application of the engineering design process, application of, problem solving skills. If they have a number, they got it. And the students rely heavily on that. And I think part of that is due to most of them having had or are in AP calculus or calculus. So they have a huge math background, which they heavily rely on. And it appears to, if we go down here to the impact, it appears that the students, like I said, are going to really rely on that quantitative aspect as much as they can because their qualitative aspects were lacking. They would provide some context. They would provide some of the why behind what they were trying to find, what they were trying to say, but it was always quantitatively based. They never tried to look purely at the qualitative aspects that make the quantitative aspects possible. So overall, it did appear that, implementation was successful in impacting application and the problem solving skills, but much more emphasis is going to need to be placed on the qualitative aspects in the future. And I think that's something that could be within the school impact, emphasizing the why behind our students' thinking, because many of our students want those concrete numbers but can't explain the why behind it. So that's not something that's only going to impact my class, but anybody in any science or any math class. We need to be looking at not only the quantitative, but the qualitative aspects as well. Thank you.